All right, welcome everyone. Today we're going to dive deep into how quantum mechanics is shaping our view of the universe.
Yeah, definitely moving beyond just those tiny particles.
Exactly. We've got this fascinating YouTube video transcript all about breakthroughs in the field.
Yeah, some really mind-bending stuff.
Oh, absolutely. We're talking about like particles linked across incredible distances, black holes maybe not being as destructive as we thought.
And even the possibility that the expansion of the universe is driven by quantum stuff.
Seriously, get ready to have your mind blown. But first,
Yeah, let's set the stage.
okay, so quantum mechanics, it's not just about the subatomic world anymore, right?
No, not at all. It's like we're realizing its influence on the largest scales imaginable.
Okay, so let's start with something I find totally fascinating. Quantum entanglement.
Oh, yeah. Spooky action at a distance.
Right. But it's not just theoretical anymore. Scientists in China actually demonstrated entanglement over 12,200 kilometers using a satellite.
Wow, that's amazing.
They sent entangled photons, those particles of light, into space and proved that they stay connected no matter how far apart they get.
It's a challenge to one of Einstein's fundamental ideas about the universe. Yeah.
He wasn't a fan of entanglement, was he?
Not really. Called it spooky action at a distance.
Mm.
But all these experiments, they've definitively shown that entanglement is a real phenomenon.
So what does that actually mean for us, in practical terms?
Well, imagine, like, communicating instantly across vast distances.
Like from Earth to a Mars colony or something.
Exactly. Unhackable, instantaneous communication. That could be a reality.
That is mind-blowing.
And the implications go way beyond communication. Think about computing, cryptography even.
It really makes you question the nature of reality, doesn't it? Is everything connected at some deep level?
It's a profound question.
Okay, let's shift gears for a sec and talk about black holes. We used to think of them as just cosmic vacuum cleaners.
Right, just sucking everything in.
But they're turning out to be way more complex than we thought.
Definitely. And our source material hints that black holes are deeply intertwined with quantum processes.
One key idea here is Hawking radiation, right?
Yes. That's the idea that black holes actually slowly evaporate because of quantum fluctuations near their event horizons.
So they're not just sucking stuff in, they're kind of leaking energy back out.
In a way, yes.
Mhm.
And the amazing part is scientists are now trying to recreate those event horizons in labs.
Seriously, how do they do that?
You're using ultra-cold atoms to simulate the conditions near a black hole, hoping to observe something similar to Hawking radiation.
Wow. If they succeed, what could that mean?
Oh, it could revolutionize our understanding of gravity, time, maybe even tell us what happens inside a black hole.
And there's this idea of primordial black holes too, right?
Yes, these are hypothetical black holes that might have formed from quantum fluctuations right after the Big Bang.
So black holes carrying quantum minerals of the universe's birth.
It's a fascinating idea. If they exist, they could hold clues about the early universe, the conditions back then.
A window into the beginning of time. Amazing. Now let's talk about another big mystery. Dark matter.
Right, that elusive stuff that seems to make up a huge chunk of the universe.
Could quantum mechanics explain that too?
Well, one leading theory suggests that dark matter is made up of these weakly interacting particles called axions.
Axions, okay. But they're really hard to detect.
Extremely difficult.
Hmm.
But scientists are using some incredible quantum tools to try to find them.
Like what kind of tools?
Things called axion haloscopes and interferometers. These highly sensitive detectors that can pick up the faintest signals from axions.
So are we close to actually figuring out dark matter?
It's a really exciting time. These new quantum tools give us unprecedented sensitivity. A breakthrough could be just around the corner.
Wow, I'm already feeling my mind expanding.
Just wait, there's more.
All right, let's go even further back to the very beginning, the Big Bang. Could that even be influenced by quantum mechanics?
Well, the idea is that quantum fluctuations during the universe's rapid expansion, called inflation, could have seeded the large-scale structure of the universe. Like galaxies and clusters, everything we see today.
So tiny quantum jitters determine the entire cosmos.
That's the idea, and it's pretty mind-boggling, I know. To study this, they're using complex simulations, even creating something called hyperbolic lattices to model the quantum states of the early universe.
And the expansion of the universe, it's accelerating, right? Could quantum fluctuations be driving that too?
It's possible. Those tiny energy fluctuations we talked about earlier, they might be the force behind dark energy, pushing galaxies apart faster and faster.
So microscopic quantum jitters are deciding the fate of the entire cosmos. That's a lot of responsibility.
It really puts things into perspective, doesn't it?
It's incredible to think that quantum mechanics isn't just about tiny particles. It's a fundamental force shaping the universe on the grandest scales.
Absolutely. And we're just starting to understand its implications. The more we learn about quantum mechanics, the more we see how it's woven into the fabric of reality itself.
This is all so mind-blowing. I think we need a moment to process everything.
It's wild to think that these quantum phenomena aren't just happening in like black holes or across the universe.
Right. It's happening right under our noses, practically.
Yeah, like the transcript mentions this experiment where they recreated the conditions of interstellar space.
Super cold, super empty, that kind of thing.
Exactly. And they found that complex molecules form way faster than we'd expect.
If we were just thinking about classical physics, you mean?
Right. It all comes down to quantum tunneling.
Ah, quantum tunneling. That's where particles can sort of tunnel through barriers they shouldn't be able to cross.
Yeah, it's like they cheat the system. And in interstellar space, that means reactions that might take millions of years can happen much quicker.
So are we saying quantum tunneling could be responsible for, like, kickstarting the chemistry that leads to planets and life?
It's a fascinating possibility. And the transcript even highlights how it's crucial for the existence of stars.
You're talking about nuclear fusion, right? The process that powers the sun.
Exactly. For fusion to occur, protons need to overcome their repulsion and get close enough to fuse.
And quantum tunneling helps them do that.
It's the key. Without it, stars wouldn't be able to ignite.
So it's like the universe has a quantum cheat code to make stars happen.
I like that analogy. And speaking of stars, we can't forget about neutron stars.
Those incredibly dense remnants of massive stars.
Yeah, they're like giant laboratories for studying quantum mechanics in extreme environments.
The transcript mentions superfluidity, that bizarre state where matter flows without any resistance.
And it's been observed in neutron stars. It's mind-boggling.
It's like a fluid that flows forever without slowing down.
Exactly. And then there are pulsar glitches, where a neutron star's rotation suddenly speeds up.
Like a star hiccup, but a quantum one.
And those glitches are giving us clues about the inside of neutron stars, how matter behaves under extreme pressure.
It's amazing that we can use these distant objects to study fundamental physics, but quantum mechanics goes even further, right? The transcript suggests it might even explain the accelerating expansion of the universe.
Right. We talked about those tiny energy fluctuations, and they might be the driving force behind dark energy.
So those microscopic quantum jitters could be determining the fate of the entire cosmos. That's a lot of power for something so small.
It's a profound thought, and it gets even weirder. The transcript mentions vacuum transitions.
Vacuum transitions, what are those?
It's the idea that the universe could suddenly shift to a lower energy state, maybe even changing the laws of physics as we know them.
Whoa, that sounds like something straight out of a sci-fi movie.
It does, right. And the transcript suggests it could happen through quantum tunneling. The whole universe tunneling to a new state, like flipping a cosmic switch.
Okay, my mind is officially blown. We've gone from molecules in space to the fate of the universe.
And there's more.
More. Bring it on. I think I can handle it.
All right, remember how we talked about entanglement and how Einstein called it spooky action at a distance?
Yeah, and how those scientists in China proved him wrong with their satellite experiment.
Well, in 2024, researchers at CERN, using the Large Hadron Collider, observed entanglement in top quarks.
Top quarks. Those are the heaviest particles we know of, right?
Exactly. And they found that these massive particles, even as they were flung apart at almost the speed of light, could remain entangled.
So even in the realm of high-energy physics, entanglement still holds sway.
Absolutely. It gives us a glimpse into how quantum mechanics might have worked in the very early universe just after the Big Bang.
So are you saying the early universe might have been this giant web of entangled quantum states?
It's a possibility that many physicists are considering. And the transcript describes another experiment where they entangled pairs of heavy ions to test quantum communication.
Could this be the key to interstellar communication, like Star Trek level stuff?
It's not as crazy as it sounds. This research could lead to space-based quantum communication systems.
Imagine sending a message to a distant star and getting a reply instantly. But what does this tell us about reality itself?
That's the big question. If particles as massive as top quarks can be entangled, it suggests that quantum mechanics is even more fundamental to the universe than we thought.
Like the universe is whispering its secrets through entanglement.
It's a beautiful way to put it. But the transcript doesn't stop there. It goes into exotic states of matter.
Okay, I'm all ears. Exotic states of matter, you say?
Not just solids, liquids, and gases. We're talking about things like Bose-Einstein condensates or BECs.
BECs, okay. What are those?
Imagine a bunch of atoms cooled down to ultra-low temperatures, so cold they behave like one giant quantum superatom.
Like they all meld together into a single entity.
Exactly. And scientists are now creating these BECs in space on the International Space Station.
A quantum physics lab in orbit. What's so special about BECs?
They offer a unique window into the quantum world on a larger scale,
Yeah.
helping us understand how quantum mechanics affects matter in extreme conditions.
Um.
And some physicists even believe that BECs could hold clues to the mysteries of dark matter.
Dark matter, always popping up.
Right. It seems like quantum mechanics is everywhere we look in the universe.
It really does. But the transcript also mentions another exotic state of matter, quark-gluon plasma.
Oh, yeah, that one sounds like something straight out of Star Trek.
It does, doesn't it?
Quark-gluon plasma is thought to be the state of matter that existed in the very first moments after the Big Bang.
Wow, so like fractions of a second after the universe began.
Exactly. It's a kind of primordial soup of quarks and gluons, the fundamental building blocks of matter.
But how can we even study something that existed billions of years ago?
Well, scientists have figured out a way to recreate it.
Seriously?
They use powerful particle accelerators like the Large Hadron Collider to smash heavy ions together at incredible speeds.
So like creating a miniature Big Bang in the lab.
That's the idea. And it lets us study the properties of quark-gluon plasma, learn about the fundamental forces of the universe.
That's amazing. But hold on, it's not just limited to labs, is it? The transcript suggests that quark-gluon plasma might also exist naturally inside neutron stars.
You got it. Those super dense neutron stars we talked about, they're not just quantum laboratories for superfluidity.
They're also cosmic pressure cookers, creating quark-gluon plasma.
Exactly. Extreme environments that allow us to observe physics we could never replicate here on Earth.
This is blowing my mind. And there's more, isn't there? The transcript even talks about something called synthetic quantum dimensions.
Ah, yes, synthetic dimensions. Now we're getting really futuristic.
It sounds like science fiction.
It does, but it's real science happening right now.
Okay, so what are synthetic quantum dimensions?
Scientists are using lasers and ultra-cold atoms to create artificial dimensions in the lab. It's like expanding the space that quantum particles can move in, giving them more freedom.
It's like they're building extra dimensions into reality.
In a way, yes. It's a new way to explore quantum mechanics in more complex environments. See how particles behave when they have more freedom.
So why are they doing this? What's the point of creating new dimensions?
It can help us understand some of the biggest mysteries in physics, like dark matter, dark energy.
Maybe even wormholes.
Well, that's a long shot, but who knows? That's the beauty of science. Every discovery opens new doors, new possibilities.
The world of quantum mechanics is full of surprises.
Absolutely. So we've gone from these tiny particles linked across vast distances to the possibility of creating new dimensions in a lab.
And it's clear that quantum mechanics isn't just some weird theory.
It's a fundamental force shaping the universe, from the smallest scales to the largest.
Mind-blowing.
The most exciting part is that we're really just getting started. Every discovery raises more questions, pushes the boundaries of what we know.
It makes you wonder what other mind-blowing discoveries are out there, just waiting to be found.
This deep dive has taken us from the heart of stars to the very edge of reality. And it's clear that the exploration of quantum mechanics is far from over. If quantum mechanics can influence the evolution of stars, galaxies, even the universe itself, could it also play a role in the emergence of life? That's something to think about. Keep asking questions, stay curious, and who knows what incredible discoveries await us in the future.